Hello and welcome to this section on mechanics and motion. Before we do any mechanics and motion, we must really take a look at vectors and try to develop an understanding of them so we can actually start doing some physics. We begin by just simply asking, what is a vector? Well, a vector is a quantity that has both direction and magnitude, and this is in contrast to a scalar, which only has magnitude. The best way to illustrate the difference between the two is if we consider speed and velocity. Speed is a scalar and it only tells us about the magnitude. For example, we can say that we are traveling at 1 meter per second. Now, this is useful, but sometimes we need information about our direction as well. And velocity, we would be talking about traveling 1 meter per second at some speed in a given direction. So, for example, we could be saying that we are traveling at 1 meter per second in the eastbound direction, or northbound, or west, or northeast. It doesn't really matter, as long as we know the direction. And that's why we're talking about velocity. So we know the speed at which we are traveling and where we are going. And that is useful in life. I'll just zoom in on this. As you can see here, I've drawn some axes with a red arrow. And this red arrow is our vector. And I will call this vector V. And I will denote that this is a vector by drawing a little arrow above it. And this is just a notation that we use. To be complete, we'll just label our axes X and Y. Now, we've already talked about velocity and speed. Now we have our vector V, and this would be velocity. But we can also have speed, and this is the magnitude of the velocity, or the magnitude of the vector. And the magnitude of a vector is indicated by these vertical lines on either side of the symbol. But how do we express direction for a vector? We need to look at something else first, and that is the definition of a unit vector. A unit vector is just a vector that we define as lying along the axes. So we've got a green one to indicate the unit vector that lies along the x-axis. And we will call this I, and we indicate it's a unit vector with a little hat above it. And then we define another unit vector which lies along the y-axis. And we indicate that this is a unit vector with a little hat. And we call this unit vector j. Okay, so how do we express those vectors in terms of these unit vectors? Well, we can drop a line down from the tip of our vector down to the x-axis. And we know that this is some distance along the x-axis. And we will call this Vx, or the x component of the vector. Now, given that our unit vector I has a length of 1, we can express the x component, or how much we are moving along x in our vector, as Vx multiplied by I hat. And we can do the same to describe how far we are moving along the y direction. And this is Vy. And we express that by adding the y component and multiplying that by j hat. So this is saying that I have moved a number of units along x, and I have moved another number of units along y. So I've previously used the example of speed and velocity, and I said that speed is the magnitude of velocity. So in our vector, we've already written down that we have some magnitude here. So how do we find what this magnitude is? Well, if you look at this whole thing, this just looks like a triangle. And we know Pythagoras' theorem. We know that we have this hypotenuse, we have the opposite, and we have the adjacent. And we know that the hypotenuse squared is equal to the adjacent squared plus the opposite squared. And we know that the adjacent is equal to Vx. and that the opposite is equal to Vy. So from all of this, we can figure out that the magnitude of a vector is given by the square root of the x component squared plus the y component squared. Okay, let's clear this out. But let's turn this around. Let's say we know the magnitude of the vector, but we don't know the components. Well, as long as we know the angle between the x-axis and the vector, then we'll be fine. Because then we can just use trigonometry, and it is pretty trivial to see that Vx is equal to the length of the hypotenuse, which is the magnitude of our vector, multiplied by the cosine of that angle, and then the y component of that vector is equal to the magnitude of the vector multiplied by the sine of that angle. Now this is interesting because here we are expressing our vector in terms of magnitude and angle, and actually this leads to polar coordinates, and we will go through that in a different video perhaps, but this is quite an interesting thing to stumble on. So that was the basic definition of what a vector is and what information you can gather from that. In the next section, we will start looking at some operations and what we can do with these vectors. Okay, so in the previous video I did, we covered some of the basics around vectors, and now we are just going to address some practice problems around this. So I've written two problems here that we want to solve. The first problem is that for a vector v, which has components of 3 along x and 4 along y, what is the magnitude of this vector? And then we want to find what the angle is between the vector and the x-axis. The second question is for a vector with a magnitude of 3 at an angle of 30 degrees or pi over 6 radians from the x-axis, find the x component and the y component of this vector. Okay, so let's have a look. So we start with the first question. We ask, what is the magnitude of this vector? So in the previous video, we kind of covered how you can make triangles out of these vectors. And we can just do that by dropping down a line from the point of the vector down to the x-axis. And what we can see here is that this is the x component, and this distance is the y component. And we know from Pythagoras' theorem that the square of the hypotenuse of the triangle, which is in this case the square of the magnitude, is equal to the adjacent side squared plus the opposite side squared. So in this case, the square of the magnitude is equal to Vx squared plus Vy squared. Now in the question, we see that Vx is equal to 3 and Vy is equal to 4. So we substitute that in and we find that the square of the magnitude is equal to 3 squared plus 4 squared, which is 9 plus 16, which is equal to 25. So the square of the magnitude is equal to 25, and therefore the magnitude is equal to the square root of 25, which is equal to 5. So we are just going to fill that in there. Next, we want to find what the angle between the vector and the x-axis is. So we are interested in this angle. Now from our trigonometry, we know that tan of the angle is equal to the opposite divided by the adjacent. So in this case, that is equal to Vy over Vx. And then we can rearrange that a little bit, so we have theta is equal to the arctan inverse tan of Vy over Vx. And we plug that in our calculator, and we find that that angle is 53.13 degrees. Excellent. So that is 53.3 degrees. Okay, I have cleaned my board, so it is time to address the second question. So here we have a vector with magnitude of 3, and it is at an angle of 30 degrees or pi over 6 radians from the x-axis. So we know that we have this vector and we know that angle, and theta is equal to 30 degrees or pi over 6 radians. And we also know that the magnitude of that vector, or this distance, is equal to 3. So how do we find the x component? Well, we previously found from our little triangle that the x component of any vector is equal to the magnitude of the vector multiplied by the cosine of the angle between the vector and the x-axis. So this is 3 times cosine of pi over 6. So Vx is equal to 3 times, well, cosine pi over 6 is root 3 over 2. And that is our x component. And we can do the same thing for Vy, but in this case it is V times the sine of theta. Now here we have 3 again and sine of pi over 6. And sine of 30 degrees or sine of pi over 6 is just half, so this is equal to 1.5. And that's it. This is all pretty simple, pretty straightforward. You can probably find more examples or make more examples up yourself and just practice it. And that's one of the key things with this, is practicing it, so it all becomes second nature. Okay, in the previous video we had a look at some of the basics of vectors, and now we are going to look at how to add 2 vectors. So on the screen I've already drawn one vector, and we call this vector u. Now I will just write that down in terms of the components. So if we drop down to the x-axis, we see that this distance has ux. And if we drop across to the y-axis, we see that this distance has uy. So we can write our vector u in these terms. Ux multiplied by I hat plus uy multiplied by j hat. But now we take a second vector and we call that vector v, and that is equal to vx multiplied by I hat plus vy multiplied by j hat. And we want to add this to u. We want to find out what u plus v is equal to. So how do we do this? Well, we start graphically. When we add 2 vectors, we take the first vector, and from the tip of that vector, we start drawing the second vector. And let's just put that second vector there. Now we want to find that x component, Vx, so we drop from the tip all the way down, and we measure the distance from the start. So this distance is Vx. And we do the same thing along y, and we find that this distance is Vy. Now when we add the 2 vectors, we draw the resultant vector from the base of the first vector to the tip of the second vector. And this vector is u plus v, and little arrows above it. And to find the components of that vector, we drop down to the x-axis, and we find that that distance is equal to ux plus vx. And we go across to the y-axis, and it wouldn't surprise you that this distance is uy plus vy. So when we write that out, we see that the x component of this vector is equal to ux plus vx, all multiplied by I hat, and then the y component is uy plus vy multiplied the j unit vector. And I'm just going to clean this up, and we are now going to look at scaling vectors. So we have this vector, and we will call that vector u again. And then we have another vector we call a, and that is equal to some constant, which is just a scalar value, multiplied by the vector u. Now, what is the resultant vector? Well, let's just set c as equal to 2. And we go and drop down u. I am going to call that ux is equal to 1, 2, 3, 4. And uy is 1, 2, 3, 4. Yeah, so uy is equal to 4. Now what this constant does, it scales that whole vector. So this is like saying a is equal to 2 times uxi plus uyj. And as we know that these are both 4, we can expand that out to get 8i plus 8j. So when we scale a vector by some scalar, we uniformly scale that all directions. Okay, and now we are going to have a look at some special cases which may shine a bit more light on why we use the notation for the vectors that we do. So here we have some axes. So now I'm going to just draw some unit vectors along the x-axis and a unit vector along the y-axis. And I'm going to call the one along the y-axis j and the one along the x-axis I. I'm now going to take some vector which is p, and it is some scalar quantity a multiplied by I hat. So that is saying that p is a times this. Okay? Then we take another vector which is q, and that is some scalar quantity b times j hat. So q is b times this vector. Okay, so here we are just scaling 2 vectors. So let's draw p. And let's draw q. But now we want to find another vector, and this is the vector r. And we define this vector as p plus q. So we do that same vector addition again, starting at the point or the tip of p. We then draw the vector q. There we go. And then our vector r will be drawn from the base of p to the end of q. And this is r. But when we write that out, so r is equal to p, but we know that p is equal to ai, and then plus q, but q is equal to bj plus bj. We now realize that a and b are actually the x component and the y component of r. And I hope that this kind of demonstrates that whenever we write a vector down, the notation where we have some value followed by some unit vector plus another value followed by some unit vector, it actually all originates like this. Every vector can be expressed as the sum of the unit vectors scaled by some quantity. Okay, we've had a look at how to scale vectors and how to add vectors. Now we're going to look at some problems just to practice the skills that we developed. So we have this problem that given the vectors u is equal to 2 times the unit vector I plus 4 times the unit vector j, and v is equal to 4 times the unit vector I plus 3 times the unit vector j, compute the following. We have u plus v, the magnitude of u plus v, 2 times u, and the magnitude of 3u plus 2v. So we begin with the simple vector addition. We have the vector u, which is equal to 2 times I hat plus 4 times j hat. Next we have our vector v, and that vector is equal to 4 times I hat plus 3 times j hat. Okay, fantastic. And we now add these two together. So we add the 2 and the 4 to get the x component of u plus v. And that is 6 times I hat. And then next we add 4 and 3 to get the y component. And that's 7 times j hat. Wonderful result. But now we want to find the magnitude of this vector. And we know that the magnitude of a vector squared is equal to the sum of each component squared. So we take our first component, which is 6i, that is 6 squared. And then we have our second component, which is 7 squared. That's 36 plus 49, which is 85. So u plus v, and the magnitude of that squared, is equal to 85. So the magnitude of u plus v is equal to the square root of 85. Okay, quite straightforward. And the next one is also quite straightforward. We have our vector u, and we multiply that by 2. So we have 2 times u, or that is equal to 2 times, open the brackets, 2 times I hat plus 4 times j hat. Now all we need to do is figure out what 2u is. We multiply that out, so that's 2 times 2, and that's 4 times I hat. And then the next one is 2 times 4, so that is 8 times j hat. And that gives us our vector 2u. Finally, we have this problem which is designed to consolidate these two concepts of adding and scaling vectors. And we start off here by just figuring out what 3u is equal to. So we have 3 times u, and that is equal to 3 brackets, and we have 2 times I hat plus 4 times j hat. Okay, and we just multiply that out, so we have 6 times I hat and 12 times j hat. Okay, so that is 3u. Next, we want to figure out what 2 times v is. Well, we have our vector v, and we have this little 2, so we stick the 2, open some brackets, we take the first component of v, which is 4 times I hat, and then we take the second component of v, which is equal to 3 times j hat, and we perform that same multiplication. We have 2 times 4, so that is 8 times I hat, and we have 2 times 3, and that is, of course, 6 times j hat. So these are our vectors we are interested in. But now we add them, so we have that 6i and 8i there, so that becomes 14 times I hat. And then next we have 12 and 6, so we have 18 times j hat. So this is our vector 3 times u plus 2 times v. But we want to find the magnitude of that, and we know that the magnitude squared is going to be equal to the sum of the components squared. So this then given by 14 squared plus 18 squared. And I will peek at the calculator and know that this is 520. And that results in 3u plus 2v, and the magnitude of that being root 520. That is roughly 22, I believe. Okay, and that was it. Thank you very much, and until next time. In the final section of this introduction to vectors, we will discuss vector multiplication. Because there are two ways to multiply two vectors. First, we have the scalar product, and then second, we have the vector product. The scalar product is also called the dot product, and that is because we denote it with a little dot. In contrast, the vector product is also called the cross product, and that is because we denote it with this little cross. And this is an important point to remember, is that whenever you see two vectors being multiplied with this little symbol, then you know we are talking about the cross product. Now, the scalar product actually takes its name from the fact that the output is a scalar, whereas the vector product, the output is a vector. Scalar product, the computation is very simple. However, for the vector product, it is a bit scarier, as you can see here. Now, this notation has a very specific meaning, and we won't really go into what it all means. I am just going to show you how to perform the computation. If you are really interested and want to do some deeper reading, then I'll just give you the hint that this is called the determinant of a 3x3 matrix. Okay, and we will start with the definition of the scalar product. So let's say we have two vectors, u and v, and we are taking the dot product. Then what we do is we take the x component of u and multiply that by the x component of v. And then we add the product of the y component of u and the y component of v. And that's it. That is the definition. Okay, but what does the scalar product actually mean? Well, let's take the vectors that I've drawn on screen. We have u. Now that is clearly ux I hat plus uy j hat. But remember that uy is equal to 0. Next we have v, which is vx I hat plus vy j hat. So now we take the dot product of the two. U dot v is equal to ux vx plus uy vy. But remember that uy is 0, so this cancels out. But if uy is 0, then that must mean that ux is equal to the magnitude of u. So we can replace ux with the magnitude of u. And if we remember from our fundamentals, Vx is equal to the magnitude of V multiplied by the cosine of the angle between V and the x-axis. So we replace Vx as well. And in this case, we see that the angle between V and the x-axis is the same as the angle between V and U. So the dot product of two vectors is the product of the magnitude of the two vectors and the cosine of the angle between the two. So does this always hold? If we just draw an arbitrary vector u and an arbitrary vector v, you have to remember that the direction of the axes are also arbitrary. And this always holds. And if you're not convinced, you can just practice this yourself. But now, what if we set the magnitude of u to be equal to 1? What happens then? Well, u dot v is equal to u v cosine of theta. Well, this u then falls away because it's equal to 1. And we see that we have the x component of the vector v. Or if we think about all of this, it is the component of v that lies along U. So another way of thinking about the dot product is that the dot product represents the component of one vector that lies along the second vector multiplied by the magnitude of that second vector. Okay, and we now move on to this scary cross product. This does look pretty terrifying if you're not familiar with the notation, and we are just going to go through how to perform the computation. We won't really go into what it means. The biggest thing about cross products is that they are tedious and not particularly difficult. And as long as you can spot the pattern in the computation, you will be alright. So there are 3 steps, and the first step is where we take the unit vector I, and then we concern ourselves with all the other components that are not in the same row or column as I. We open some brackets, multiply that by I hat. And what's the computation we perform? Well, we take the product of the top left and the bottom right, and from that we subtract the product of the bottom left and the top right. And that's our first step. For the second step, we add a minus sign. And let's get rid of this for a moment. And we take the second unit vector. And we take all the components that are not in the same row or the same column as that unit vector. And we perform the same thing. So we have unit vector j. We take the top left and the bottom right. We multiply them together. And then we subtract the product of the bottom left and the top right. Now we add a plus sign. Rub this out, and I'm sure that you are familiar with the pattern now. We take this unit vector and we only work with the components that are not in the same row in the same column. We take the top left, multiply that by the bottom right, u, x, v, y, and we subtract the product of the bottom left and the top right. And we fix our brackets. And that is how you perform the cross product. But let's tidy this up. So now I've tidied it up and it's all typed up and nicely shown at the top of the screen. And now we consider the vectors that I've drawn on the screen as well. Now we've got some vector u and we've got some vector v. Now I would like you to imagine that even though we have an x-axis and a y-axis drawn on the screen here, I would like you to imagine that there's another z-axis which is coming out of the screen towards you. The unit vector associated with z is k hat, and that is this one here. Now for simplicity, we will define u such that uy is 0 and uz is also equal to 0. So u purely lies along the x-axis. Now we've got the other vector v, and the x and y components have some finite value, but we'll set vz equal to 0 as well. The reason why we're doing this is that this allows us to cancel anything out in this big scary line, anything which has a uy or a uz or a vz. So that is that, and that. You see, the important thing about maths is always make your life as easy as possible. So now we are only left with that bit here, so we will write that out again, and that in our case u cross v is equal to ux vy, and that's multiplied by k hat. Now if you remember how I defined u with no y component or a z component, we find that the magnitude of u is also equal to ux. So we can perform that substitution again. If we go back to our definitions of vectors, we remember that vy, or the y component of v, is equal to the magnitude of v multiplied by the sine of the angle between the vector v and the x-axis. So we can substitute that in there, and that is the result of our cross product. But you'll notice that we still have this unit vector k. And this indicates that the result is still a vector. And in this case, where we have u and v all lying in the same plane as the screen, the resultant vector sticks out of the screen towards you. And this is a key result. And that is that the cross product of two vectors is always perpendicular to both component vectors. But there's also something interesting, and that's the direction of the resultant vector, because it has to lie along that z-axis, and I've just said it comes out of the screen. What is stopping it from going into the screen? Well, this is the right-hand rule, and this is a fun little exercise. I'm going to draw some arbitrary vector u and some vector v. So there we go, and that's u. Sure, we do the arrows. Now take your right hand and extend your index finger to lie along u, and your middle finger to lie along v. And now extend your thumb. In what direction does the thumb go? But now reverse the situation and extend your index finger along v and your middle finger along u. In what direction does your thumb point now? And this indicates something very important. And that is that u cross v is not equal to v cross u. And this is something you wouldn't have encountered before in a multiplication, because you've always been used to, let's say, a multiplied by b, that being equal to b multiplied by a. But in the case of vector products, u cross v is equal to minus v cross u. Okay, so this was all the basics around vectors. I will do another video where we take some practice problems involving the dot product and the cross product. But once you have a good grasp of how these computations are performed with vectors, you'll be surprised how far you can get with physics. We have just gone through a video where we discussed vector multiplication, and now we're just going to do some exercises to really solidify the skills that we've learned. So in this practice session, we are going to take the problem shown on screen. We're taking the vectors. A is equal to 2 times the unit vector I plus 1 time the unit vector j, and b is equal to minus 2 times the unit vector I plus 5 times the unit vector j. And then we have the third vector c, which is equal to minus 4 times the unit vector I plus 10 times the unit vector j. Given these vectors, we have to compute a dot b, or the scalar product of a and b. We then find the angle between a and b. We compute the cross product of a and b. Then we show that a cross b is equal to minus b cross a. Then we show that a cross b is perpendicular to the vector a. And finally, we show that c is parallel to b. So let's start with the first part, and that is we have a vector a, which is equal to 2 times the unit vector I plus 1 time the unit vector j. We then have our vector b, which is equal to minus 2 times our unit vector I plus 5 times the unit vector j. Then the dot product of a and b is equal to, well, we take the x component of a and the x component of b and we multiply them together. And to that we add the product of the y component of a and the y component of b. So that is equal to minus 2 times 2, so that is minus 4. And to that we add 1 times 5, so that is 5, and that is equal to 1. So that is our first answer. We'll just write that there because that will come in useful later. The next part is where we find the angle between a and b. Well, if you remember, the dot product a dot b is also equal to the product of the magnitude of a and the magnitude of b multiplied by the cosine of the angle between the two. So first we want to find the magnitude of A and then the magnitude of B. And from Pythagoras' theorem, we know that the magnitude of A is equal to the square root of the sum of all the components squared. So we have 2 squared plus 1 squared. And that is, of course, equal to root 5. So next we want to find the magnitude of the vector B, and that is equal to the square root of minus 2 squared plus 5 squared. And when we plug that into a calculator, we get the square root of 29. Then our next step is to multiply the magnitude of A with the magnitude of B, and that is root 5 multiplied by root 29, which happens to be root 145. So if we look back at A dot B is equal to, well, root 145 times the cosine of the angle, we divide both sides by the root of 145. So that cancels out. And we've already established that A dot B is equal to 1. So the cosine of the angle is equal to 1 over root 145. Or the angle is equal to the inverse cosine of 1 over root 145, which is equal to 94.76 degrees. Wonderful. And I just realized I've written off screen a little bit, so I'll move that up so you can see. Right, so we can now write the angle between that. By the way, this is also 1.653 radians. Now I'm going to rub most of this out to make everything nice and tidy, apart from that figure there. Okay, so here we've established that the magnitude of A times the magnitude of B is equal to root 145, and this will be useful shortly. Okay, so next we compute A cross B. And we already established that this is equal to the magnitude of A multiplied by the magnitude of B multiplied by the sine of the angle between the two, and then K hat. Now it is worth pointing out that this K hat only applies if A and B are purely on the XY plane. So we already know that the magnitude of A multiplied by the magnitude of B is equal to the square root of 145. And we've already got our angle, so we just take sine of 1.653 and then K hat. And when we plug these values into a calculator, we get that A cross B is equal to 12K hat. Okay, so we write that here, just so we remember that for later. And let's get rid of all of that again. So next, we want to show that A cross B is equal to minus B cross A. Right, and we're going to take a different approach this time. So here we take minus B cross A, and then we draw our box, and we take I hat, J hat, K hat, and we add a minus sign in front, and then we write minus 2, 5, 0, because there is no K component here, and then 2, 1, 0, because also there's no K component there. Alright, so the first step is to take that unit vector and everything that is not in that row or column. So that is I, and open some brackets. That's 5 times 0 minus 1 times 0. And we then subtract, and we go to the next bit. So we take J and everything that's not in that row or column. So J hat, and then we take minus 2 times 0 minus 2 times 0 plus. And then finally, we take that k hat and everything that's not in that row or column, and we get k hat minus 2 times 1 minus 2 times 5. And that's it. Well, we can see that that is 0, that is 0, that is 0, that is 0. And then we find out this is minus 2, and then we subtract 10. So this is equal to minus 12, but we still have this little minus sign here that we ignored, so that cancels that out. And this is then 12k, and that is equal to that. Fantastic. So next, we want to show that A cross B is perpendicular to A. So how do we show that? Well, if we think about the dot product of some vector, let's say u dot v, we said that that is equal to the magnitude of u multiplied by the magnitude of v multiplied by the cosine of the angle between the two. Now, when u and v are perpendicular, the angle is 90 degrees, and cosine of 90 is equal to 0. So this is how we can test. We can take the dot product of two vectors, and if the result is 0, we find that they are perpendicular. So let's test this. So what we do is we take A dot, and in brackets, A cross B. Now we already know that A cross B is equal to 0 I hat plus 0 j hat plus 12 k hat. And we know that A is equal to 2 times I hat plus 1 times j hat. So when we take A dot A cross B, we take the x components, so that's 0 times 2. And we take the y components, that's 0 times 1. And we take the z components, well, that is 0 times 12. And we add them all together. But that is 0, that is 0, that is 0. So all of that is 0. And indeed, they are perpendicular. So finally, the previous question already gives a hint as to what you can do with the final question. How do we show that B is parallel to C? Well, with the dot product, we had a vector u dot v, and that is equal to the product of the magnitude and the cosine of the angle between them. But when we had u cross v, that was the product of the magnitudes and the sine of the angle between them, and then some unit vector perpendicular to both other vectors. Now what happens to theta if they are parallel? Well, theta is equal to 0, and sine of theta is equal to 0. So if B cross C is equal to 0, they are parallel. So let's check that out. B cross C. Well, we draw our matrix I, J, K. Then we take minus 2, 5, 0. They are the vector components for B. And then we take C, it's minus 4, 10, and 0. So we perform the operation again. We multiplied that by some stuff we do here. So that's I times 5, 0, minus 10, 0. Oh, look, that's already 0. And the next component. There we go. So we have minus j multiplied by well, minus 2 times 0 minus 4 times 0. Oh, that's also 0. Finally, we take that k hat and all the bits that are not in that row or column. So we get k hat, we multiply that by minus 2, 10, minus 4, and 5. Well, what do we have here? Well, that is minus 20. And then there's a minus sign, and that's also minus 20. So that becomes a plus sign, and that is also equal to 0. So therefore, we can show B and C are parallel.